Let me just share the screen so that we know where we stand. Yeah, we can maybe start off. Hi everyone. Good morning, good afternoon, and good evening to whichever part of the world you are. Welcome everyone to today's session on end-to-end machine learning model building. So today we will be just a brief introduction for those unattended. We are this session is a part of our Machine Learning Bootcamp, which we are doing in collaboration with AI Engineering YouTube channel by Srinivasan Srivatsan. And today we will be discussing about end-to-end machine learning model building by taking an example of a real-world dataset. We'll be using a dataset of a hospital where they are trying to improve patient care conditions by looking at historical survival rates of the patients. Okay, so we'll be developing a model that will predict the chances of survival of a patient based on care conditions, patient demographics, and patient's previous conditions. Okay, so just to be on the same page, so it will be a hospital data set. We'll talk about it in a while as well. So the standard approach that we would be following to solve the problem is basically we will be defining the objective, and then we will be looking at the data requirements and data collection. However, these two things are not required as we already have the data with us. So I'll talk about a real world case study on how the data requirements are given and how we do the data collection as well in a while. Okay, at the end of the session, I'll discuss a real world case study as well. Okay, and then we'll go ahead with exploratory data analysis, data pre-processing, and then building a model, evaluating it, optimizing it. And then the later steps are putting it to production and monitoring. So that's something that we won't do in this session. For that, we'll have another session in the coming week. Okay, so with that, I'll probably get started. And yeah, I hope there are no connection or no issues. But yeah, Gunika, can you just confirm if everything is fine?
Yeah, it's fine.
Yeah, great, perfect. Okay. Great. With that, let's get started. So first things first, let's try and understand the problem statement better. Okay. The goal of building this particular model, right? It is to actually we want to build a model that will allow us to predict the chances of survival of a patient after 1 year of treatment. Okay. Now, what is this 1 year of treatment? Okay. Okay, the data set that we will be discussing about, some of the meta information of the data set is anonymized owing to some privacy concerns. So for the sake of simplicity, let's imagine a cancer treatment hospital in the province of Greenland has been trying to improve its care conditions by looking at historic survival of the patient. Basically, they are looking at their data but couldn't identify what are the main factors leading to high survival rates of the patients. Okay, and they have the following data dictionary. One is they have ID of the patient care situation. They have diagnosed condition, which says that the diagnosed condition of the patient, and they have ID of the patient. They have treatment with drugs. Basically, it says class of drugs used during the treatment. So basically, if someone is getting treatment with cancer, they might be given some drugs as well, right? So some medicine. So that's what they're talking about. And they're talking about the patient age, patient body mass index, and they have also given a data whether a patient is a smoker or a non-smoker. They also have the data of whether a patient stays in a rural area or a urban area of the country. Okay, and they have also given some previous conditions. Basically, they have given the condition of the patient before the start of the treatment. Okay, and also so it's actually this variable is split into 8 columns: A, B, C, D, E, F, Z. And also there is an additional column called as number of previous conditions, okay, which is a summation of these 7 columns basically. And there comes our target variable, that is survived 1 year. Okay, if the patient, basically that states that if the patient survived after 1 year or not. If it is 0, it means that the patient did not survive, and if it is 1, that means that the patient has survived. Okay, now that we have these data points, our objective is to basically, let's presume that we are the best data scientists out there in Greenland, and the hospital has hired us to solve this particular problem. Now it is our responsibility to develop a machine learning model that will predict the chances of survival of a patient after 1 year or not. Okay, so we need to predict whether, given the data points of a patient, our machine learning model would predict whether a patient would survive or not after a year based on their conditions and medications that the hospital is using. Okay, so yeah, and with that, let's do some hands-on session. Let's get into the hands-on side of things. So we already have a notebook. Okay, I'm sorry, I'm just scrolling up. Okay, so first off, we already know what we want to do. We know the objective. We have the data, and we also have the data set, right? So first and foremost, we'll be loading all the libraries that we would need for running this analysis. Okay, first off, we'll be having pandas, numpy, matplotlib, seaborn, and sklearn, and the model evaluation metrics that we might want to use. We'll be loading all those libraries so that we don't get any errors when we try to run such things. And then we try to load our data. Here we are basically calling pd.readcsv and giving the link to the dataset, raw GitHub link to the dataset, so that we can load our data. And first and foremost thing, we are trying to explore the dataset, right? So what we have done here is we have used the method.head and try to check what all data points our data has. As we just saw, there is ID, patient care, diagnosed condition, and so on and so forth. Treated with drugs, I can see that there is something called as DX6, DX2, DX6, DX1.
Hi, Chanukya. Can you please zoom in a bit?
Yeah. Yeah, so it will reflect in 10 seconds on YouTube. So I zoomed in, so yeah, it should be fine.
Yeah, great.
Okay. Yeah. And coming to patient age, right? So we have a column name called as patient age. And yeah, where we are having the age of the patient. There is body mass index. Okay, so we have all these data points as we discussed. Patient, rural, urban. It is it is basically giving us an information whether a patient is in urban locality or a rural locality. Okay, and it is also giving about the patient mental condition, stable. And there are 8 columns. These are nothing but the 7 columns, which are the previous conditions. And we are also calculating the number of previous conditions. That is nothing but the summation of these things. So as you can see, there is 1 and 1 here. So we are adding these 2 data points and having the number of previous conditions is 2. And in this second data point, we only have 1. So we are only seeing 1 here. Okay, and the survived 1 year is 0 or 1. If it is 0, then the patient has not survived. If it is 1, the patient has survived. So this is the data description, and yeah, this is a high-level overview of how the data is looking. And if we go to the exploration, right, when we run .info method, okay, so we can already see that. Okay, so these are the counts of each of the columns. So diagnosed condition has 18477 rows, and everything is non-null. There are so similarly, now we can see the value counts for all the variables. Okay, as you can see, we can see the entire data set here. And as we go further, as we go further here, we can see that data.describe, right? So we can see the descriptive statistics of the data set, okay, clearly. And now we will be splitting our, first and foremost, we'll be splitting our data into train and test data. Okay, we'll be running our model on train data set and testing our model on test data set. Okay, so basically once we build the model, we'll be applying it on our test data set and see how it is performing. Okay, so that's some context about what we are going to do. But before that, let me just run our data set once again. Yeah. There are in total 23,097 entries. And out of which, so for these values, right, A, B, C, E, F, Z, we can see that there are some null values because the total count is 23,097, whereas here we have 21,862 or so. Okay, so there are some missing values for sure, which we will be treating in the next iteration. Okay, when we are doing the data cleaning. So coming to the training and testing split, right? So first and foremost, we will split our data into train data set and test data set. Okay, and we'll be building our model. So we'll be keeping the test data set completely separate. We won't touch it. Okay, and we'll be building our model on the train data set. So let's do that. First and foremost, we are splitting in our features and target variable. Here our target variable is survived 1 year. So we are putting it as Y, and all our input features are going to capital X. So this is where we'll be feeding all our input features. And then in the next iteration, what we are trying to do is we are basically splitting our data into train and test, and that too we are giving a test size of 0.2. That means that our train data will have 80% of the data, and our test data will have 20% of the total data set. And if you look at it, so there is another thing that we have used that is called as random state. Random state is used more for reproducibility of the results. So for example, if I'm running this particular piece of code, I should get the same train and test data set, and you should also get the same train and test data set, right? So that it is consistent all across. So in order to make it more consistent, the shuffling more consistent, we'll be using random state. And coming to stratification, right? So stratification, so what happens is, if we look at the problem, right, we are predicting whether a patient has survived or not. It is 1 or 0, which means that it's a classification problem. So what happens is, typically in some of the classification, some classification problems do not have a balanced number of examples for each class. Okay, when I say balanced number of examples, let's say if you have a sample of 100 data points, and let's say you have let's say 100 t-shirts. Okay, out of those 100 t-shirts, 90 t-shirts are of large size, and 10 t-shirts are of medium size. Now in this case, if we look at the examples, 90 of the t-shirts are medium and 10 are only 90 of them are medium, and the remaining 10 are large, right? So there is a huge class imbalance in this case, because 90 are medium and 10 are only large. So there is a huge variation, right? So similarly, when there is a huge class imbalance, that's where what we try to do is we try to stratify. We try to split the data set using a stratification method, something called as a stratified sample splitting. Okay, so that we maintain the proportion of the data set. So that will allow us to preserve the proportion of the examples for each class label. Okay, when we use this stratification splitting. So that's some context. And I think we have also played around with this fraud detection data set, which is also kind of imbalanced data set. So yeah, even there, we would want to maintain that proportion, and that's where we would be using the stratification. Okay, so that's some context on train and test split. Okay, and after that, what we will do is we will do the data pre-processing and explore the data as well. Okay, now we are trying to explore xtrain.head, and we are trying to see, yeah, so basically we have already split the data set, right, into train and test, and now we are exploring the train data set. Okay, so again, we try to check how is our data set looking. So as you can see, like, we have fetched the entire first 5 rows of the data set. And after that, we are also trying to check the xtrain.info, right, to check if there are any null values or not. Okay, as we can see, there are some null values here, A, B, C, D, E, F, Z. There are definitely some null values. Okay, so there is some missingness. We need to fix that missingness, and we also get to see the type of the data set. That is, there are some integers, some objects, some of the data points are float. So we'll also go through it in detail in next few minutes. So our observations are, there are 18,477 observations divided into 17 columns. Okay, and there are some missing values in the data set, definitely. As you can see, there's 18,000, whereas there's 17,000. So there is definitely some missingness. And let's also look at the distribution of the target variable, right? Our target variable is survived underscore 1 underscore year. So let's look at it. So in order to do that, we just need to use this particular piece of code from yeah, so basically we need to use it from Seaborn library. Okay, so don't worry about the code. Code is very simple, and as data scientists, we don't really need to worry about the frameworks. All we need to do is we need to understand the process and how effectively. So it's data science is all about solving a problem with the help of data in a scientific way, right? And in the process, if you have to build new frameworks, or if you have to use some other tools, let's say R or Python or anything of that sort, you should be prepared to do that. Okay, and code is something that you can easily Google and get it. So don't get too much into the code side of parts. Anyway, like, we will share this code with you. So we are using a Seaborn library here to understand the distribution of the target variable. So as we can see in the train data set, the people who survived are considered as one. And as we can see, 12,000 patients, close to 12,000 patients, right? They have survived. And close to maybe somewhere between 6 to 8,000, they have not survived in the train data set. So it's almost a proportion of 1:2, or like, maybe 1.2:2, I would say, because it's slightly above 6,000, and it is slightly the number of people who survived, that is one, slightly below 2,000, 12,000. Okay, so the ratio would be around 1:2 or 1.2 or 1.3:2. So we don't really need to treat the class imbalance. However, I would always recommend you to experiment and see if it really changes the result. So feel free to do some class imbalance treatment. So data science is all about experiments and iterations and everything, right? You keep experimenting with things and see if it is working in your favor or not. So feel free to do it as an exercise. Okay, but in my opinion, like, it is not required in this case. Okay, and coming to box plot, right? So once we have looked at our target variable, let's also look at the box plot. When we are looking at the box plot, we will be looking at the continuous variables of the data set. Okay, and usually box plots are are a nice way to visualize and explore outliers. I'm not going too extensively into the outlier treatment at the moment, but we'll discuss about it. So with this piece of code, as you can see, we are only picking those variables: diagnosed condition, patient age, patient body mass index, number of previous conditions. So we have only picked those variables which are numeric in nature. Okay, and then we are trying to check their representation of the box plot. Okay, so how do we know whether they are numeric or categorical? We can simply look at dot info, or probably we can also look at this data, right? Dot head. With dot head, we can simply say, okay, ID patient care, there is a diagnosed condition. Okay, treated with drugs is a categorical variable. Patient age is a continuous variable. Patient body mass index is a continuous variable. Patient smoker is a categorical variable. Why is it a categorical variable? Because it says it's yes or no. Okay, it's a category. Whereas patient mass index is continuous because it's a numeric value and it is continuous. It is something like numbers, right? 1, 2, or 10, 20, 30, and so on and so forth. Okay, so that's some context about continuous and categorical variables. So we have plotted the box plot of all the numeric variables that are of relevance. So as we can see, for diagnosed condition, we don't really see any outliers out here. However, for patient age, that too for patients who survived, right? We can see that there are some outliers. Now, what are these things? Let's look at it, right? So patient age, 0 years, 20 years, 40 years, 60, 80, 100, 120. So we can see that there are some outliers where patient age is above 100 or maybe 110 or so. So these are some outliers. Now you can technically treat them. Okay, I think Aarti has delivered a great session just a week ago where she has brilliantly explained about how to treat outliers. Okay, there are different ways to treat outliers. One is you can remove them, or you can treat it in a different way. I wouldn't recommend you to remove, but you can try it out. You can try it out and see if it is really helping or not. Okay. So similarly, I can see that patient body mass index. Okay, patient body mass index, again, 0, 5, 10, 15, 20, 25, and so on. So technically, I think there is a cutoff value for patient body mass index. So as data scientists, right, so we should also understand each and every data point very well. So let's try and search what is minimum value for BMI. Okay. Commonly accepted BMI ranges are underweight, under 18.5. Normal is 18.5 to 25. Overweight is 25 to 30, and so on. Okay, so this is the typical BMI ranges. However, as we can see here, the BMI range is below 5, which is practically may not be possible. And also, if I look at it from a subject matter expert, if I look at it as a doctor, maybe it doesn't make sense, and I'll probably recommend to remove these values or treat them so that we fix those values. Okay. So I'll leave it to you on the outlier treatment because you have extensively done it in the previous session by Aarti. So I'll leave it to you guys. Same with the number of previous conditions and all. Okay. So with that, I'll probably let you people do the exercise to treat outliers and see if it improves the performance or not on the overall model building part side of things. This exercise, you can take it later, okay, for your self practice. Okay, and then what we also did is we plotted a correlation matrix. Okay, to check if there is any correlation between these numeric variables. We can see that there is very minimal correlation. So yeah. And then now let's look at the categorical variables. So far we have looked at the numerical variables, right? Let's look at the categorical variables too. And first and foremost, yeah.
Hi, Chanukya. Sorry to interrupt. There are a lot of questions about why we first split the data and then handle the missing values. So maybe you can go over it once again, just give an explanation about why we did so.
Yeah, so typically, right? So generally, whenever we perform some analysis, we try to so this is something that is widely talked about, where we try to basically we keep our test data out of the entire model building process, right? Otherwise, like, if we expose it in the model building step, so it will also lead to some what you call data leak. Okay, there could be a potential data leak, and you might end up giving your model, giving information about your test data to your model, right? So that would also increase biasness and all. Again, I'll talk about this extensively in a while at the end of the session. So yeah, I'll definitely address this.
Yeah.
Okay.
Okay.
Yeah, I'll do that. But yeah, I'll add it at the end why it is being done this way. Okay, in the industry, so what you do is basically you split the data, train and test, and you don't touch the test data set. Okay, so you religiously don't touch it, so that you're not really taking any information from the test data set into your model building process. So if you are doing that, there will be an information leak which will eventually lead to bias, and when your model is exposed to a very new unseen data set, right, it will go bonkers. Okay, so again, I'm not saying like it is it will have a huge impact. Okay, the impact may or may not be imminent. We'll discuss that later. Okay, so yeah, that's some context. Again, coming to box plot, right? Okay, just give me one moment. Yeah. So now finally we will be looking at our categorical variables too. Okay, xtrain. So here we are basically doing trying to check if there are any null values or not. Okay, in our xtrain data set. So here, as we can see, that there are 12 null values for treated with drugs, and for A, B, C, D, E, F, Z, we have some 995 missing values. Number of previous conditions too, we have 995 missing values. Now, how do we treat these missing values? Okay, 95 missing values, number of previous conditions. Yeah. Now, how do we treat these missing values? So as we look at it, coming to treated with drugs, right? It's a categorical value variable, and for categorical variables, it makes more sense to go with mode. Okay, so in this case, what we are trying to do is we are filling this missing value with mode. Okay, and similarly, the remaining variables, right? A, B, C, D, E, F, Z. They are also categorical variables, and we are just filling them with mode again. Okay, and coming to, yeah, so that's how we have filled the data, fill the missing values, and now we are left with number of previous conditions. So this is another variable that is we are left out with. Technically, this is a number of previous conditions is a numeric variable, so it makes more sense to go with mean or median. Okay, or the other way of doing it is we can simply add A, B, C, D, E, F, Z, and the summation will be the number of previous conditions. Okay, so that is another way of looking at it. However, like we have treated it here with mode for simplicity, because we have already treated all these variables with mode. So technically, it will be the same. However, we will change the code later where we will show the summation. Why are we even doing this? Because this is something that is already described in the data description, where it was told that previous condition, number of previous condition, is nothing but the summation of A, B, C, D, E, F, and Z. So it is nothing but the sum of all these variables, right? So we have treated them with mode. So technically, the value for this also will be mode. So that's why we treat it with mode. But however, you can change it to the summation of all these variables. Okay, we'll change the code later on that particular bit. So that's how we have treated this missing value with mode as well. Okay, so that's some context about how we tried to treat missing values in this data set. Okay, now let's look at it further. now the next challenge is to build a model, right? Before even building a model, what we will have to do is we'll have to technically, we'll have to ensure that all the data points are numeric in nature before even putting into the machine learning model, because that's what machine learning models take, right? So they can't really take the categorical variables or strings or anything of that sort. So we need to change each and everything into uh, basically numeric values. So let's see how to do that. Okay. And before doing that, we are also trying to check what are the unique values of each and every variable that we have, each and every feature that we have. And when we try to run this particular code, right, we are trying to check what are the unique number of data points in each and every column or in each and every variable. For ID patient care situation, there are 23,097. That is like on the overall data set. So this is for the overall data here, as you can see. Okay, and for patient ID, it is 10,000. Okay, for treated with drugs, there are 32 unique values, which are categorical values. Okay, for patient smoker, there are 3 unique values, 3 unique categories. For patient rural urban, there are 2. That is whether a patient is from rural or urban. Patient mental condition is 1. Basically, like everyone, I think, like there is no other value, so we can simply remove it from the data too. But yeah, let's not arrive at any conclusion there. And remaining variables, we have 2 as the unique values. And survived 1 year, again, it has 2 unique classes, because a patient would survive or not. Okay, there are only 2 cases in there. Yeah. Yeah, so that's some context. And then yeah, and coming to treated with drugs, right, as we can see, so whenever we have whenever we have more classes, right, what we try to do is we try to go with this technique called as one hot encoding. I think this is something, again, like we have discussed in our data preparation session, where we generally go with one hot encoding, where when we have nominal data points, okay, which has no order. Okay, so coming to patient smoker, so there are 3 categories, right? We can technically go with one hot encoding, and it would create two more new features. Okay, so technically there will be 3 features for patient smoker, and similarly for patient urban, it will also one hot encode, and it will create another additional feature, and so on. But coming to treated with drugs, right, there are 32 variables, 32 unique categories. And if we do one hot encoding, it will additionally create 31 new features, right, which is massive. And I think, like it will expand our total number of features massively, which will make it around 50 or so, if I'm not wrong, because already we have some 17 features, and adding some 30 plus would make it above 50. Okay, before we dive deep into it, let's understand what is one hot encoding, right? So for example, let's take this example where we have 2 columns, ID and color has only 3 categories, 3 types of colors, that is red, blue, and green. Okay, if the color has only 3 colors, color column has only 3 colors, red, blue, and green. And when we do one hot encoding, right, what happens is color will basically will end up creating 3 more new features, that is color red, color blue, and color green. Okay, so we will end up creating 3 more new features. And what will happen is, when there is red, it will give you 1, and when there is no red, then it will give 0. So in this particular case, color red is 1, because in this particular row, for the ID 1, there is red color that is already allocated here. So that's why it is 1. And color blue and color green are 0. Similarly, for when we do one hot, and I mean when we are going to the second cell, right, second row, the color red is marked as 0, and color blue is marked as 1, and color green is marked as 0. Why? Because the second cell is attributed as blue, and so on and so forth. So for green, again, like, you'll only see that color green feature has 1, and remaining the rest of the features are categorized as 0. Okay, so this is what one hot encoding is, and we technically use it for nominal data without any order. Okay, basically here there is no order, right? Red, blue, green, you don't have any order. However, if you are talking about let's say college grades, okay, someone who is getting an excellent grade is probably, like, put on top, right? And there will be something called as A grade, B grade, C grade, D grade. So it has some order. Okay, whereas in here there is no order for colors. Okay, so there is no specific order. So in such cases we use one hot encoding, and when there is some order, then we go with ordinal encoding or label encoding. That's something that's not required in our case. Okay, so for all these features, right, which have more than which have 2 or more categories, we will go with nominal encoding, or basically we will go with one hot encoding. Okay, and coming to treated with drugs, there are 32 unique entries. Okay, unique categories. We will see how to solve it. Okay, either one way of approaching it is we just go with one hot encoding and create 31 additional features. Okay, that is one way of going ahead with it, but there might be some other optimal way, right? We will see if there are any optimal ways. Okay, so there is definitely an optimal way, as we can see here. Okay, so what we are trying to do is we are separating all the strings and treated with drugs by a space, and we can easily, like, identify that there are only 3 drugs that the patients are given: dx1, dx2, dx3, and dx6. Okay, so these are the 6 different types of drugs which are being given to patients. So a patient is under a medication, and they might get 1 drug or 2 drugs or 3 drugs, or a combination of more, right? So this is the total unique values of that particular category treated with drugs. So dx6 drug is given to 6,861 people, dx5 drug is given to so many people, and so on. And a combination of dx1, dx2, dx3, dx5, and dx5 is given to 3 people. So these are the total value counts of each of those combination of drugs. Okay, now what we are trying to do is we are trying to create unique entries of these drugs, of individual drugs, that is dx1, dx2, dx3, dx4, dx5, and dx6. Okay, so what has happened is, instead of having one single column for a combination of drugs, what we have done is we have created 6 new features, and each having dx1, dx2, dx3, dx4, dx5, dx6. And if a patient is consuming 4 types of drugs, then they will be there, then in that particular position, right? If they are taking, let's say, dx1, dx2, dx3, then it would be somewhat like this. Okay, dx1 will be shown as 1, dx2 will be shown as 1, and dx3 will be shown as 1. Okay, and for this particular cell, this particular patient is taking a combination of dx1 and dx3, and for this particular cell, this patient is only taking dx5 drug, and these two patients are only taking dx6 drugs. Okay, so that's how, like, we are optimally doing it. Instead of going for 31 additional features, what we are trying to do is we are only going for 5 additional features here. Okay, so that's how we have treated this particular class, treated with drugs. Okay, and now we'll be entering. Okay. Yeah. Now we'll be going to, yeah. So we are done with this, right? So we are basically done with treated with drugs. And now the practical next step is to go to the, okay, just give me one moment. I think I can't see Gunika in there. Yeah. Yeah. Yeah, I think she's back. Yeah. Sorry for the trouble. Yeah. So now that we are done with we are done with one hot encoding for treatment with treated with drugs variable. Now we'll be going to the rest of the variables. Let's say, like, we have patient smoker. Okay. Here we have again, like, we have three different categories. Okay. Whether no, yes, and cannot say. Okay. So coming to no means that the patient is not a smoker. When they say yes, that means that the patient is a smoker. And when they say cannot say, they don't know whether a patient is a smoker or not. Okay, so that's the third thing, that the third category that they have. So what I've done here is have considered cannot say as no. Okay, which is the maximum value of the three categories. Okay, so I can still keep the category, but for the simplicity to reduce the number of features, I've just gone with no for the moment. Why did we even do it? Because we are just going with the mode of these three entries. So that's it. Okay, you can still keep it the same. There is no harm in it. But this is one way of optimizing the total number of features. But yeah, again, if a subject matter expert says that okay, this is extremely important class, then we will retain that. However, here I don't really see much prominence. Okay. And now coming to patient mental condition, it has only one category. Okay, so technically it won't add much value to your model, because each and every entry in the dataset is the same. Okay, it is a stable condition, so we will drop that. Okay, and with that, it will leave us with these data points. Okay, with these bunch of data points. And now what we are trying to do is we are also doing one hot encoding for patient smoker and patient rural urban as well. Okay, and we are trying to check we are trying to see our data set, how it looks like. Okay, and yeah, that's some context. Okay, now we don't have any null values in our data set because we have treated each and every null value. At the same time, we have also converted all the categorical variables to numeric variables. Okay, so in total, right now we have 23 columns. Earlier we used to have 17 columns. Now we have 23. Okay, and also there is no missingness. As you can see, each and every uh, column count is 18,477. Okay, so yeah, with that, so with this, like, we are done with the data pre-processing or data cleaning of our trained data set. So we'll be applying the same steps to the test data set too. Okay, so that this way, like, we are not really spilling any information between train and test data. Okay, so we have done exact same steps of missing of filling the missing values, or converting the categorical columns to numerical columns and everything. So we have taken the exact same steps. And why did we even do this splitting in the first place, right? Training and testing data set, so that we don't really spill any information. Okay, between while we are modeling, we don't want to spill any information of test data set into train. Okay, I'll give you an example here. So for example, if we are taking the entire data set and trying to treat missingness, so what will happen is you are basically, let's say, like, we are taking a particular variable. Let's take an example of age. Okay, let's imagine age has some 20% of missing values, okay, on your entire data set. So in that case, what we will do is we will probably we will probably fill the missing values with the median of age, right? So we are taking the entire data set mean. Okay, and we will be feeding that, will be filling the missing value with the mean of that entire column of patient age. Okay, and then after that, if we split the data set into train and test, technically we are already passing some information of test data set into train data, because we have done the splitting after imputing the values. So technically you are passing some information which can lead to some bias. I'm not saying it will definitely lead, but just to keep the sanity in place, we have done the train and test split separately right at the beginning. Again, there is people even do it otherwise also, where they try to split the data set after cleaning the data, let's say after filling the missing values and doing all sorts of things. But again, it's not highly recommended. Okay, so usually, on most of the articles we see that. But at the same time, if you look at the data science competitions, right, if you look at the data science competitions on DPhi or on Kaggle, they give something called as train dataset and test dataset. Technically, test dataset is untouched. You're not touching the test dataset at all in the entire process. Okay, on any platform, on any data science platform, they give two different datasets: train and test. Train is the dataset on which you perform the analysis, and test is the dataset on which you try to apply all the pre-processing steps again and try to predict the uh, final model prediction, right? So that means that you are maintaining that sanity already. Okay, so similarly, when it comes to industry, what we try to do is we try to ensure that we don't spill any information of training and of model. We don't want to spill any information of test data in the model building process when we train the data set, when we train the model. Okay, I'll also give you some analogy by taking an example at the end also, if it is still not clear. Okay, and coming to checking missing values, right? So basically we are applying the same steps to the test data set, though this can be done at the end. We just did it here so that it's easy for us later on for building the model. So I'm just skipping this step because we have done the exact same steps for the train data set. Okay, I'm just quickly going over this, and now comes the model building part. So the first thing that we have done is we have gone with a logistic regression. Okay, and I'm not getting into the details of logistic regression right now, but we have built a logistic regression, and this is how it is. And we try to predict the model. We try to predict its performance on the test data set. And here, as you can see, we have already built the model. We have called it as model is equals to so and so model.fit and logistic regression. And here we are trying to predict its performance on the test data by test. Okay, and and on the new test data. Okay, so we are trying to predict it on the test data, and the performance is 78.78. The F1 score is 0.78. And similarly, we have also built another model, a random forest. Okay, for random forest, we have basically taken some parameters as well: random state, n estimators, and maximum depth. These are some things which we have taken randomly, but we can also optimize. I think we have also already discussed that in Raviraj's session, where he has shown how to tune the hyperparameters, right? So we have also added that code on how to tune it. We'll talk about tuning in a while. Okay, and we have built a random forest classifier, okay, by using these parameters, and try to evaluate on our test data. And when we are trying to evaluate on our test data, the performance was 0.82. Okay, and now comes the third step, that is we have used random forest and Boruta. Okay, Boruta. What is Boruta in the first place? This is something I'm sure, pretty much most of you might have heard for the first time, but some of them who have attended the previous boot camp, data science boot camp, might be well aware of this particular feature selection method called as Boruta. So I'll quickly go over what is feature selection and explain what is feature selection and feature importance. Okay. So as you can see, right now we have close to 23 variables, right? 23 features. Okay. Basically, there used to be days where people used to use linear regression aggressively, and even now, there are some industries who still use linear regression. Okay, and those are the gone days where you have only 5 features to fit your linear regression model. Okay, and now coming to the modern data sets, right? If I talk about fraud detection data set, there will be hundreds of variables. Okay, and if I'm talking about our current data set, there are 23 features already. And if I would have gone with the treatment with drugs as pure one hot encoding, it would have bumped our total number of features to 57 or so. I mean, it will be beyond 50. Okay, so a data set would have 50 or more features, and we might be dealing with millions of observations, right? Okay, right now we have only 20,000 or 30,000 observations, but we might also be working with millions of observations when we are talking about fraud detection data set or e-commerce data set and so on. Okay, and in such a complicated case, if you are feeding all the features, it will be extremely computationally expensive. When I say computationally expensive, it will take a lot of time to run your model, and it is not very optimal. Okay, and you don't know whether all the variables that you are feeding into your model are appropriate to be sent to the model or not. So in order to solve that, in order to understand whether a particular variable or a feature is extremely important to your model or not, there are two techniques that we have. One is feature importance and feature selection. Okay, where we try to select only a set of features that are extremely important as per these techniques, and we feed them into the model. Okay, and it is also much optimal because we are not really dumping each and every variable out there. Okay, so that's some context about feature selection and feature importance. Basically, feature importance refers to techniques that assign a score to input features or features based on how useful they are in predicting your target variable. And coming to feature selection, it is a process where you automatically or manually select features which contribute most to the target variable. Okay, so where you are selecting features that are contributing heavily to your target variable, that is called as feature selection. And again, there are different ways of selecting features. Okay, I'm not getting into the details of what are the different types of it. We have another tutorial around it. We will definitely pass on that tutorial and also learning material to you. Okay, and so coming to features, right? Features and target variable, I think you pretty much know about this. So I'm just, for the sake of simplicity, I'm just taking the iris data set, where the objective is to predict which species a particular flower belongs to based on sepal length, sepal width, petal length, and petal width. So you're basically predicting which species a flower belongs to based on these features. Okay, and when it comes to feature importance, right? As I said, it gives a score to each and every feature based on how useful they are in predicting the target. So when we put all these features into the feature importance technique, or what technique, it basically gives the importance of each and every feature. Here it is saying that, okay, petal width is extremely important, and petal length is the second most important feature. Sepal length is the third important. Sepal width is the fourth. So this is how it is categorizing when it comes to feature importance. Okay. And coming to feature selection, right? Okay. So in short, so basically, with the help of feature importance scores, you will try to perform feature selection. Okay. So what feature selection does is, so here we already know that sepal width is not that important. So feature selection, be it like, there can be manual or automatic processes. So in the case of manual process, what we'll do is, hey, sepal width is not that important because my feature importance score is not that great for sepal width. So that's why I would go ahead with selecting only sepal length, petal length, and petal width as my features. Okay, so this is a manual way of selecting features and performing your model. Okay, and now, why do you even need feature selection? I already spoke about it, where if you're dealing with a very large data set and very large number of features, again, optimization and computational cost, everything is extremely important, and you don't necessarily need to feed in each and every data point, right? Just because you have the data points, it doesn't mean that you dump it into the model. You need to learn as a data scientist and know which features are important for to solve a particular problem. And also there will be something called as curse of dimensionality. I'll probably leave it here. The curse of dimensionality is nothing but, let's say, like, you have a big cricket ground or a football ground, and you have uh, put your keys somewhere. If you have thrown your keys somewhere in a particular football ground, and you are given a task to search that particular key, okay, in a single playground. Okay, so you will still be able to search all around and manage to find it somehow, right? But however, even that, it's very difficult. However, if you are given, like, there are 10 playgrounds and you randomly threw your keys somewhere, and you don't even know in which playground did your key fall into, and you are asked to search, then it is like extremely difficult for you to search for your keys, right? Because you have to go and check in the first playground, and then go to the second playground, and then go to the third playground, and so on. It's extremely difficult. So that's an analogy where the searching becomes very difficult, because there are many dimensions. So similarly here, there is, when we talk about dimensions are nothing but features. Okay, so we try to keep it minimal, and, like, try to optimize that by keeping into a picture of the optimization, and also yeah, and also the computational cost into picture. We want to keep it as small as possible. And why feature selection? One is, it removes irrelevant features, and it increases the performance of the models, makes the training faster. Okay, because you have less features, your training becomes super fast. It's easier to build, easier to understand. Why is it easier to understand? If I say that, like, there are 50 variables, and the importance of this particular variable is this, and it is reacting this way, it's extremely difficult, right? Whereas if I have only very limited features which are talking about the importance of a particular problem, then it's much simpler to explain, it's much simpler to interpret, and it goes well that way. And it's also easier to debug. Okay, so that's some context about why feature selection is required, and what are the benefits. It reduces overfitting, it improves model performance, it reduces training time. Okay, it's more to do with optimization, costs of basically computational costs and others. Okay, and coming to setting up of experiments, right? So you have the data set, you split it into train data, test data, and then pre-process your data, and that's where you also apply feature selection in between. Okay, if you have, let's say, I'm just taking a toy example here. There are 6 features, and we are applying feature selection, and after feature selection, we only have 4 features. Okay, and you try to build various models on top of it, and try to evaluate it, and then expose it to and then predict your performance on the final test data. Okay, so that's how you can technically do. So coming to feature selection, right, you also need to apply on your this thing as well. Yeah, and today we'll be talking about Boruta. Okay, now what is Boruta, right? Boruta is a feature selection technique, which is one of the recent and most advanced feature selection methods that I had used, and also it's pretty popular, and it comes in very handy when you are dealing with large data sets. Okay, so Boruta follows this all relevant feature selection method, where it captures all features which are in some way or the other relevant to the target variable. Okay, so technically the feature selection techniques prominence is nothing but you need to select apt features from a bunch of features, right? So all you need to do is you need to build an algorithm or a technique in such a way that you want to capture those features that are extremely important to predict your target. So that's the main objective. So in this case, what Boruta is doing is it is following an all relevant feature selection method, where it captures all features which are in some way or the other relevant to the target. Now, how is it doing is something that we need to understand. Okay, we'll see how it is doing. So let's say again here we have taken a very toy data set which has three variables. Let's say age, height, three features: age, height, and weight, and we are trying to predict the income. Okay, this is a pretty bad example, but again, let's just take it as an example for the moment. Okay, we are taking these features: age, height, and weight. Okay, and we are trying to predict the income of an individual. Okay, so merely consider this as an as a toy example. Okay, and now what does Boruta do? Okay, so what Boruta does is, firstly, it adds a randomness to the given data by creating shuffled copies of all the features. What does it mean? Okay, so basically we have age, height, and weight as our features, right? And we know that our target variable is income. Okay, now what Boruta is doing is it is creating some shadow features. Okay, so basically it is creating a synthetic data of age which is called as shadow age, and it is also creating a synthetic variable of height which is called as shadow height and shadow weight. Okay, so you're duplicating your data. Okay, so firstly, it adds randomness to the given data set by creating shuffled copies of all the features. In other words, basically it is creating the duplicates of your data set and also shuffling the values in each column. When I say shuffling the values in each column, that is nothing but you're shuffling the values in let's say shadow age. Okay, you're shuffling the values of all the age column within it. Let's say 51 is appearing here, whereas it is appearing here now. Okay, so you're just simply synthetically creating it and you're shuffling within the column itself. Okay, and then it trains on a random forest classifier on the new data set. Okay, right now I'm just giving an example of random forest classifier because that's what we'll be using in the example. However, it also applies for XGBoost and other algorithms too. Okay, then it trains on random forest classifier on a new data set and applies the feature importance measure to evaluate the importance of each and every feature. Okay, and also it will see whether, okay, I'll just show you that. So basically it is throwing, it is putting into a random forest classifier and it is trying to predict the feature importance of each and every feature. When I say each and every feature, it means that your original features as well as shadow features that are newly created by Boruta, which is nothing but synthetic features. Okay, and that's where, okay, that's where there is a magical statistical score called as Z score. Okay, so I'll probably not get into the mathematics side of Z score. Okay, uh, so what it does is at each and every iteration the algorithm compares the Z score of shadow features and the original features to see if the original features are performing better than shadow features or not. Okay, as you can see here. Okay, so the feature importance score of original feature is 39. Okay, whereas shadow feature is 11. Okay, and the feature importance score of wait, let me just check if I can zoom in. Zoom. Sorry. Okay, I think it's better if I explain it this way. Okay, so basically, if we can see here, so it is giving feature importance score for each and every feature, including the shadow feature. Okay. So what it is trying to compare is, it is trying to compare the feature importance of age, which is with its shadow feature, and it is giving a hit called as some other, like, it is creating another measure called as hits. And if your age importance, if your original feature importance is higher than the shadow feature, then it is retaining the feature, and if not, it will probably not retain it. Okay, so it is an iterative process. It is going over this particular iteration over and over, and then finally it selects what are the best features to be put into the model. Okay, so that's some context about how Boruta works. Okay, and finally the algorithm stops either when all the features get confirmed or rejected, or it reaches a specified limit of that random forest runs into. And in essence, the algorithm is trying to validate the importance of the feature by comparing it with its shadow features. Okay, which also in a way it is creating more robustness, right? Because you are creating some synthetic data, and you are comparing your original variables with your shadow features, and seeing if a particular feature is really important or not. Okay, so there is a lot of robustness that it is bringing into the entire scheme of things, and it is trying to validate the importance of your feature. Okay, so that's some context about the intuition of Boruta, and we will probably see how to implement it. So we have given some examples as well as some references as well in the PPT. I think you should be able to see that. But with that, I'll probably let Gunika take over and show the code walkthrough of Boruta. Gunika.
Yeah.
Yeah, you can share your screen maybe.
Yeah. Is it visible?
Yes, it is visible. Yeah.
Great. Yeah. So currently we have a number of features here. So we have diagnosed condition, patient ID, patient age, and a lot of other features. And what is our target feature? Our target variable is basically predicting if the person will survive or not. Right. So as Chanukya nicely explained, we'll now be implementing feature selection. So what is feature selection? Feature selection is selecting those particular variables that actually contribute towards predicting the target variable. That is, we will select those features that will actually help us in predicting whether the person is able to survive the next year or is not able to survive the next year. Right. So for this, we actually have a number of feature selection methods, and we have provided good resources around different methods as well. Apart from Boruta that we'll be discussing today, we have recursive feature elimination, feature importance using random forest. Just give me a minute. Yeah. Sorry for the disturbance. Okay. So we were here. We'll be trying out feature selection using Boruta, which is a feature selection technique. So it is basically an all relevant feature selection method. So other methods that are most usually present, usually what they do is they try to eliminate as many features as possible that do not contribute towards predicting the target feature. But what Boruta does is it includes all the features that might have some importance, even very low importance, in detecting the target feature. So it by default, it uses random forest, although it works with other algorithms as well. So first of all, you need to install Boruta. It does not come pre-installed into the Collab notebook. You can install it using pip install Boruta. Pip is just a package manager in Python. And then you can import it. Even after installing, you need to import the package. So you can import the package from Boruta, import Boruta.py. Okay, now we come to building the actual making the actual feature selection process possible. So for that, we'll follow the steps. Like we'll first train a very baseline classifier. That is any classifier that use all the features in the data sets. So basically that we have created earlier. Then we will identify the most important features using the feature selection technique, that is Boruta in this case. And using those particular features that will be selected by Boruta, we'll be creating a new model. So let's get started with that. First of all, we are creating a general random forest classifier. You might have done that in the past, like a very normal random forest classifier with a random state of 1. You can use any random state. Then we have n estimators. N estimators is basically an argument which specifies how many decision trees our random forest utilizes. And we also have a maximum depth of the tree. Then we are creating a Boruta selector. For that, inside the Boruta pi brackets, we are first passing our model that we've just created. So we just created a random forest classifier. We'll pass that. Along with that, we are selecting n estimators as auto. That is, it will automatically select the number of trees. Verbose is nothing but just for displaying purposes. That is how much information it will print to us. And random state, as usual, is just for the duplication purpose, or for example, you're able to get the same results as your friend got. Now that we have created a Boruta selector, we'll fit it using our data. So what Boruta needs is basically a NumPy array. It accepts that only. It does not work with usual data frames. So we'll be passing our usual data along with our labels here. So as you can see, what is happening? You can see that it's iteratively performing a lot of steps. So initially, in the first iteration, it has not confirmed any features. For it, it does not know right now if any feature is important or it's not important. And it has kept all the features as tentative. So we had 22 features initially. All of them are tentative for us right now. Then we go on, we have a number of iterations here. And slowly you'll see that it has started confirming some features and it is rejecting some features as well. So we have 17 features confirmed here and it has rejected 3 features, which means those 3 features are not at all important in predicting our target variable. And we also have some tentative features here. So that keeps on going. You can see it has about 100 iterations that it can perform, or it can even stop before 100 if it is able to confirm or reject all the features and there is no feature in tentative. So here we're only performing the 100 iterations. And in this, at the end, we have confirmed that the 18 features are important, 3 features are rejected, and 1 is tentative. So that is also not selected at the moment because it was not as important as it was not selected within the 100 iterations that we performed, right? Okay, so now we'll be seeing what all features our Boruta selector has selected. So for that, checking the selected features, we have a support method. So what it does, it returns true if that feature is important, and it returns false if that feature is not important. Again, we have another method that is ranking. What it does, it assigns a rank to each of the features. So as you can see, there are a number of ranks. We have a number of ones here. We have some 2, 3, 5, 4. What is happening is only the features that have a rank of 1 will be actually important for our model, and only those features will be selected. The rest of them will be rejected. So getting the number of features using n features, we get to know that there are 18 significant features for our model. Now let's visualize it better in the form of a table. We are representing the same data, the same output that we got earlier in the form of a table now. So we have created a data frame in which we are seeing which all features has it actually selected. So we have the data frame here in which it says that diagnosed condition is important. Is the patient a smoker or is it not is important. Then some of these DX 6, 5, 4, 3, 2, 1 are important. The number of previous conditions the patient has was important, and so on. And you can see that some features like C, E, Z, and F are given lower ranking, which means they are not as important as the other features. Okay, so what was the third step? First, initially, we created a very random, a very baseline model. We created a random forest classifier. Then we created a Boruta pi object in which it selects the most important features. Now, a third step is to actually use those most important features into our model. So what we're doing is we're creating, these variables are basically for storing the data. So we are using only those data that Boruta selector has selected. only those features from the data. So as you can see from the train and test, both of those, we have only those features selected, and this is our new data that will be used from now on. Now we have the most important features. That was our aim of feature selection. Now we'll continue our usual process, and what we're doing is we're again creating a random forest classifier, and we are using only the important data that we have selected in order to train that random forest classifier. So as you can see, this is our newly trained object in which we are using a random forest classifier. And then you can compare the performances of both the models, one before when we're using all the features in our data, and one after when we're using only selected features in our data. So now it is giving us an accuracy of 85.24, which is pretty good enough. Let us see what the accuracy was before. So it doesn't necessarily mean that it'll increase only if your model is actually giving you better results, then only you should use feature selection. So for example, or maybe if you're computationally, you have low resources and you want to reduce the number of features, then also you can use it. So as we can see, we have 82.42 FN score here, 0.824, and we have the FN score of 0.852 here. So we have seen some improvement, and thus we can keep this model, which consists of lower number of features than before. Yeah. So do we have any questions around this, Chanukya?
So far, no. No, I guess. I think, yeah. Julian, Tanmay, and Ravi have already addressed it. So, yeah.
Okay.
And someone is asking, should we do scaling the features before feature selection generally?
Yeah, it'll be nice. I think like there's no set steps as to if the scaling should be done before or after feature selection, but definitely like performance scaling before might have been better.
Yeah, yeah. So scaling should be yeah. It's better if we do early on, but yeah, it shouldn't really impact much. But yeah, so
yeah,
you want to add something, or are you?
I'm done with feature selection part. Do you want to take over for the hyperparameter tuning?
Yeah, sure.
Okay.
So thanks, Kunika. So yeah, so I'll quickly go over the hyperparameter tuning part. I think this was already covered in the last session, but just to give you some more context, right? So we tried to run the fourth experiment. So the first experiment is with logistic regression, and the second one is with random forest. Third one is with random forest using feature selection method with the help of Boruta. And the fourth is where we are using hyperparameter tuning. Okay. So yeah, in this hyperparameter tuning, we have only, we were using the grid search CV method, and we were taking into consideration of three parameters: bootstrap, maximum depth, and n estimators. Okay. And we are using a random forest classifier. Okay, of course, there are many other parameters related to random forest. We are right now like only considering these three parameters, and you can play around with many more too. Okay, and we tried fitting it using grid search CV, which basically allows us to identify what are the best parameters, so that we know, okay, here there are two combinations of bootstrap, right? True and false. Maximum depth is 5, 10, 15, and estimators is 500 and 1000. That is nothing but 2 into 3 into 2. That is 12, if I'm not wrong. It is a combination of 12. And these combination of 12 parameters. So what would be the best parameter is something that grid search CV will allow us to decide. I mean, it will automate it instead of we performing it manually. Okay. So after doing grid search CV, we are able to arrive at this estimate that having bootstrap true and maximum depth as 15 and an estimator is 1000 is the best hyperparameter. And we tried to evaluate our model as well by using F1 score, and that gave us a performance of 0.856. And finally, what we have done is we have run 4 experiments, right? We tried to see what is the performance in each and every experiment. So first experiment was a simple logistic regression, which gave 0.78 on the test data set. Okay, and random classifier, forest classifier gave 0.82, and Boruta with random forest gave 0.85. Hyperparameter tuning, it gave 0.856. So it's all about experimentation, right? We keep experimenting, and we try to improve our results and go for the optimal approach that is in the best interest by taking different circumstances into perspective. But yeah, that's some context on the overall model building part. This is a real world data set, and that's how uh, typically, like, there are numerous steps in terms of data pre-processing, right? As we can see, like, the data is a little more complex. Actually, like, if we take a step back and look at the original data set, right, it will be way more different. We'll talk about how the data requirements are given and how data is collected. If I have to talk about it, first off, someone has to be concerned. So in this particular case, right, in the case of hospital who is wanting to improve their what do you call, yeah, in this case, basically the objective is to, the hospital wants to improve their patient survival rates, improve their patient care conditions, right? So first off, someone has to be, where does this problem actually start, or where does this entire notion of who has to solve this problem, or how this problem even exists, right? How did it even come? First off, there should be someone, I mean, like, maybe the leadership team of the hospital or the doctors or the administration has to be concerned about this problem, that they need to improve the patient care conditions. And who could this be? It could be leadership team or doctors or administrators of the hospital. And now the second thought is, they need to have this thought that they want to solve this problem objectively than going with some subjectivity or opinionated approach of specialists, which might lead to bias in the way you solve the problem, right? So basically, they need to arrive at this conclusion that they want to take a data driven approach to solve this particular problem, so that they can arrive at a meaningful conclusion, because it is impacting the patient care conditions, right? So that is extremely important. And after that, now comes the part of data scientists, where data scientists and subject matter experts marry, and they try to understand what are the different underlying factors that could potentially affect the patient care conditions. Okay, so the subject matter experts, when I say subject matter experts, it could be doctors, it could be someone who's working at the hospital who understands about the patient care conditions thoroughly. Okay, who's there. As data scientists, we may not have a lot of context, right? So we need to take the help of subject matter experts, and they will guide us about the possible data points that might be impactful. Okay, so they will give that entire context, and that's when, based on that, we will gather the data requirements and start collecting it. Okay, so while collecting the data, you will have to look at the historical data that was already collected by the hospital, and one might as well need to fire some SQL queries to access the data or get the data. Okay, so and then coming to the current problem, right? So basically, the doctors and the data scientists, they have, I mean, the subject matter experts and the data scientists have arrived at this conclusion that potentially there are three underlying factors that could affect this survival rate, that is care conditions, patient demographics, and patient's previous conditions. And the original data set looked somewhat like this. Okay, it looked somewhat like this. It has I mean, it was pulled from three different tables in the database. One is patient care condition, where you have only ID, diagnosed condition, ID, patient, tested and survived year, after 1 year or not. And there is something called as patient demographics. As you can see, like, you can see the worksheets at the bottom. There is something called as patient demographics. Okay, which has patient ID, patient uh, body mass index, smoker, patient, and patient mental conditions and all. And there is another data which has something called as patient ID and patient previous condition. And now this was fine-tuned a lot, and it was given as a datathon to the previous bootcamp participants. Okay, so this was the original data set, and we had to do a lot of groundwork in terms of pre-processing it before we could expose it to the participants. So that's some context on how a real world data looks like, where like, it's not very straightforward. I mean, like, you need to sit with the subject matter experts and understand the problem a bit more, and then collect the data aptly. And in some cases, you may not have the data too. So in that, probably you need to request them to log it from now on so that it can be effectively used later on. Okay, so that's some context on how a typical problem works. And also I'll also give you a very sample case on one of the problem statements that I had worked on in the past on churn prediction. Okay, so it will be a quick walkthrough again. So where we were trying to analyze the customer churn prediction to enhance the user retention of an e-learning platform. Okay, what is churn prediction in the first place? Let's imagine you're running a business. Okay, let's imagine, like, you have let's say, yeah, you're running some business and you have some 100 customers at the start of the month. Okay, and by the end of the month, and it's a monthly subscription. Let's imagine like that, like, they are paying every month some $10 to you to subscribe to your business. Okay, and let's imagine you have 100 customers at the start of the month, and at the end of the month you ended up with only 75 customers. Okay, that means that 25 of your customers have churned out. And now you, as a data scientist, need to identify what are the underlying factors that led to this customer churn. Why did these 25 customers even leave your platform or leave your business subscription? So this is the problem statement that you need to solve and understand as a data scientist. So this was a problem statement that was there, where had to work on a customer churn prediction. Okay, that too, here I have given a very nice example of where, like, it's a subscription model where they are paying. If they are not paying, that they are not subscribed to your business. So it's easy to identify whether a particular person has churned or not. Whereas in the case that I worked on, it's a free platform. It's a free e-learning platform. Okay, like DPhi is a free e-learning platform, right? Similarly, like, it is a free e-learning platform, and to identify whether a particular person has churned out or not in itself is a very big challenge. Okay, because it's not a subscription based. If someone has created the account, they will have access to that particular account for lifetime. Okay, we don't know whether they have unsubscribed or not by any means, unless and until they delete their account or unsubscribe to the emails or so. Okay, which is unlikely to happen in most cases. I'm looking at it from a broader perspective. However, there are other parameters, like, for example, if you base it on a time-bound activity, let's say the person is not visiting your website in the next 1 month, then you can technically consider them as churned customer, where, like, they haven't subscribed to your website. Okay, if they're not active on your website, then consider them as churned user. Okay, so right now the objective is to predict whether a particular to understand the customer churn prediction. Okay, so in order to do that, okay, just to keep things simple, you have 100 customers, and 75 of them are still there, and 25 of them, they have left your subscription. That means that 25 people got churned out. Now your objective is to predict why these 25 people got churned out. Okay, so in order to do that, in this particular case, we had some 2 million users, and it's an online platform which is used for coding. I mean, like, improving the coding skills. So before even arriving at the data collection procedure, right? So typically when we try to solve a problem, what are the different things that we were looking at? Okay, typically we were defining the objective. Now the objective is defined, that we would want to predict the churn of a particular, I mean, we are trying to predict the churn score, right? So that is clearly defined. Now coming to data requirements. Now, how do we even go ahead with the data requirements? Okay, so I, as an outsider, may not have much context about this e-learning platform. But people who are working out there, right, who are working at this particular e-learning platform, they might have a lot more context about it. Okay. So you will have to talk to different people, let's say the product team or the technology team and also the marketing team. Okay. So you will try to talk to different stakeholders as a data scientist and try to gather as much information as possible as you can. And then you will basically, what you will try to do is you will try to, after getting all the context from different sections, you will try to collect the data. Okay, that is, in this particular case, we tried collecting the user information, user actions. Okay, when I say user information, demographics, type of the user, whether they are a professional or a student, graduation year, work experience, and bunch of other things. And user actions, whether they are solving the problems or not, where they are participating in the challenges or not, and whether they are using some features or not, what are their ratings, rankings on the platform, and bunch of other things. Okay, so these are the different data points that a data scientist, along with the this e-learning platform team, will be able to come up with these data points, and they start collecting the data. Okay. And that's where, like, we try to define what is a churn. You also need to define what churn exactly means, right? So as I said, like, since it's a free learning platform, we need to define what churn is exactly about. In the previous case, in the previous business case, I just told that if they stop paying for your service, that means that they're churned customer. Whereas in the case of free learning platforms, users who have not participated or submitted any code on the platform in the last 1 month are considered as churned users. Okay, so that's the thing. And basically, as I said, like, the objective is to analyze the characteristics of churned and non-churned users and build a churn prediction model. And how will it help? It helps understand the hard truth about the customer retention, and it will also probably help you engage your audience better, right? If you know why they are exactly churning out, you will be able to cater them better with probably better content, or probably uh, better platform. If they're not liking the platform, you will probably improve your platform or do something else, right? So those are the different data points that you might get as a outcome of this exercise. Okay. And eventually, the existing methodology that one might be using is probably Google Analytics, or just simply firing SQL queries and trying to understand what are the different measures, or, like, what are the different things that is leading to this customer churn. However, after building a model, okay, you will be able to know exactly why exactly these people are churning out. Okay, so that's something that we will be able to do when we build a machine learning model, right? So in the first case, what we try to do is we try to identify the data, and once we identify the data, we went ahead with collecting the data. And then yeah, so there are a bunch of other things that we have done, and then eventually building the model at the end. Okay, so there is a lot of this pre-processing steps, and also understanding the business problem, right? It takes a lot more time than anticipated. So you will have to get a deeper understanding about the problem first, and you'll also need to have a deeper understanding about the data, about the platform, and bunch of other things. And then you go ahead with your model building step. Okay, so that's some context about how you typically solve a real world uh, data science problem. Okay, where you will have to use different tools, let's say MySQL, or for getting the data, and you'll have to coordinate with different people within the organization to be able to get those data points or understand more context. Okay, so that's some context about a real world case, but I'll probably, like, we'll probably write an article around this and share it. Okay, and yeah, with that, I think we are pretty much done with what we wanted to cover. And also, people have asked why we have done this basically train test splitting before and after, right? I have shared an article just now on YouTube and everywhere. It is of machine learning mastery. Okay, so here it clearly says that, Okay, after reading this article, you will understand, okay, a naive approach to preparing data applies the transformation on the applies the transform on the entire data set before evaluating the performance of the model. This results in a problem referred to as data leakage. Okay. So why? As I gave an example, right? When you are applying the transformation on the entire data set. So you have a entire data set and you are filling the missing values of a particular column with mean value of that column. Okay. Let's say like, you have already done it. And then after doing that, you're basically, if you're trying to split your data into train and test, that means that by then you have already leaked your test data into your train data set. Okay, so that's not something we should do. We should try and avoid it. Okay, so we should, I'm not sure how much impact it would have in the overall scheme of things. It's always good to experiment and see how much impact it would have. Okay, so again, like, he has clearly explained naive application of data preparation methods to the old data set results in data leakage that causes incorrect estimates of model performance. Data preparation must be prepared on the training set only in order to avoid data leakage. Okay, and he has also explained about train test splits, k-fold, cross validation, and all in Python. But it's a interesting read. I would suggest you to go through that. So always ensure that you don't leak that information. Okay, technically, if you look at any other platform like Kaggle or even DPhi, like, we try to give, even in datathons, right? We try to give those two different data sets, train data set and test data set, and test data set is untouched till the end of the till that point you build a model, right? So it's the same practice that you need to adopt. But yeah, that's some context. And yeah, Gunika, if you have any questions, we'll be happy to address.
No, we don't have any questions. Just people are requesting for the churn PPT that we will
Okay.
definitely share on the dashboard.
Okay. Yeah, I mean, like, I'll need to make some changes there. Like, there might be some sensitive information, so I'll make those changes and I'll put it across as an article or something.
Yeah.
Okay. Yeah. So yeah, I think that's pretty much. And also for those right, like, who are looking for assignment and all, please go through dashboard, and then you'll find your machine learning bootcamp, and in here you'll be able to see the assignments. Okay, so please try to finish your assignments on time so that you are able to get your to complete the boot camp and get your certificates. Okay, try to follow the sessions, try to also go through the slides. They have as much context as possible. I mean, like, it gives a very nice explanation of each and every techniques that are being applied out there, so you'll get a lot of context that way. So I would strongly recommend to go through them diligently. And if you have any questions, right, if you have any questions or if you get stuck somewhere, do not hesitate to ask us on Slack forums or on discussion forum. Please feel free to put down the questions. We have some amazing coaches out there, as you can see already, like, on the live chat we are already seeing Julian, Raviraj, Tanmay, and Gunika and Manish, and we have Asha and a bunch of other people, right, who are pretty proactive, and, like, they're upfront in terms of helping learners. And I would strongly recommend you to make most of this boot camp, and also make most of the coaches that we have around who are extremely knowledgeable, and who have this passion, and like, who wants to give back to the community by contributing as much as possible and by sharing their knowledge, right? So that's extremely important. And with that, I think I'm pretty much
There
done.
is
Yeah.
one question.
Yeah.
How can we compare these feature selection techniques to PCA and ICA?
Okay, PCA and ICA, right? Okay, that is a different tangent altogether. I'm not a okay. PCA is slightly outdated right now. Okay, principal component analysis. So what happens in PCA is, so for example, I have these. Let's say we have some 17 columns right now, right? So in PCA, what happens is these 17 columns are then transformed into totally new features. which can be 3 new features or 4 new features or whatever it is. They're called as PC1, PC2, and PC3. So you're technically you're transforming your entire data, and you in the process you might also miss out some important information. So PCA is slightly outdated right now. It's not being used in the industry for sure. So yeah, it's kind of it is also a dimensionality reduction technique, but not so much important in the industry right now. Yeah.
Yeah, I think that is all.
Yeah. Thanks, one and all, for patiently listening to the session, and I hope you'll submit your assignments on time and also complete the bootcamp successfully. And thanks a lot, to all the coaches out there. Yeah, take care.